In our first video on Lewis structures, I talked about the rules of coming up with Lewis structures, and in particular, at the end of a Lewis structure, you were supposed to check for what was called an octet, right? Do all atoms have 8 electrons? And that works for most of the Lewis structures, but we want to learn rules about what's called formal charge, because this is how we really get the best Lewis structures out of a set of options. So coming back to our original set of rules for the Lewis structures, like I said, it's this octet check that I really want to look at, and I want to learn about formal charge. So here's an example. This particular one is carbonyl chloride, COCl2. And if we start with the Lewis structure of carbonyl chloride, we begin by counting our valence electrons, carbon, oxygen, and 2 chlorines, to find out that there's 4 from carbon, 6 from oxygen, 7 times 2 from the chlorines, so 14 up to 24. We put our least electronegative element in the center, so we put the carbon in, and then we put the oxygens and the chlorines, shooting for symmetry. We start with single bonds, 2, 4, 6. We fill up the most electronegative elements next, so chlorine, and we fill them to 8. So chlorine has 2, 4, 6, 8, 2, 4, 6, 8. And then oxygen, let's take a quick count. I've given away 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So I still have 6 left. And if I do that, and I put them on oxygen, and I do my octet check, oxygen and chlorine both have octets, but carbon doesn't. And so we think about what we did in the last video and say, well, one of these bonds needs to be converted into a double bond. I need to erase a lone pair, and I'm going to draw a second structure. I need to erase a lone pair and turn it into a double bond. So do I do it on the oxygen, erase a lone pair and put in a double bond here? Or do I do it on a chlorine, erase a chlorine and put a double bond? Both of those have octets satisfied, but only one of those structures is correct. And in fact, it's this one. And formal charge is going to tell us why. Formal charge is a measure of the number of valence electrons that a substance has, and then we take away half of the electrons in bonds and half of the lone, or the whole number of lone pair electrons. And to be honest, my super handy informal rule is just to say number of valence minus number of lines minus number of dots. So back in that carbonyl chloride structure, remember this one was one of our structure options. And if I look at oxygen, I see that oxygen touches 4 dots and 2 lines. And so oxygen would have a formal charge of 6 valence electrons from the periodic table, minus 2 lines, minus 4 dots. It has a formal charge of 0. So oxygen, I'm going to put a little 0 next to for formal charge. The chlorines they have 7 valence electrons in the periodic table. They touch 1 line, and they touch 1, 2, 3, 4, 5, 6 dots. They have a formal charge of 0 as well. So I put nice little zeros next to all of those. And then the carbon touches 4 lines, and it has 4 from the periodic table. So this is a structure where all of them have formal charges of 0. That's good because everything in the molecule has to add up by its formal charge. So if the molecule has a charge of 0, adding all the formal charges had better also go to 0. But let's go back to our other option. If I look at the other structure where I stuck, oops, I'm so used to the right structure that I drew the right structure without thinking. But remember, I put a double bond here and a single bond here. And we had drawn a structure like this. In this structure, if I look at carbon, Carbon has 1, 2, 3, 4 lines. So 4 valence electrons from the periodic table minus 4 lines that it touches equals 0. Chlorine touches 1 line, 1, 2, 3, 4, 5, 6 dots. So 7 from the periodic table minus 1 line minus 6 dots. That one has a formal charge of 0 as well. But the other chlorine, look at it, it has 2 lines and 4 dots. So 7 minus 2 minus 4 equals plus 1. This chlorine has a plus 1 formal charge. And the oxygen touches 1 line and 1, 2, 3, 4, 5, 6 dots. So oxygen equals 6 valence electrons minus 1 line minus 6 dots equals -1. And that's where we see the problem, right? It's still a structure where the formal charges add up to 0 because plus 1 and -1 make 0. But when I pick a Lewis structure, I want to minimize the formal charge. And so I look at my 2 structures and I say, well, the structure that I outlined in green on the right has some formal charges that aren't 0. I could make a better structure by doing this. And so that structure, the one with the double bonds where I minimize the formal charge, I got everybody down to 0. That's the one that I want the most. Assigning formal charges is an important skill to have. Remember, number of valence electrons from the periodic table minus the lines it touches, minus the dots it touches. And when you make Lewis structures, get all of those formal charges as close to 0 as possible. Let's try some practice. So here's a set of practice. I've got aluminum trichloride and SO2. Pause the video, give this a try, and let's see what happens. Here are the best Lewis structures that I come up with that minimize formal charge. And if I were to go through these, I would find that for aluminum, in aluminum trichloride, there's 3 valence electrons from the periodic table. It touches 3 lines and 0 dots, so this has a 0. And similarly for each of the chlorines, because they all act the same, look at, they all have the same view, they all have a single bond and 3 lone pairs. Chlorine is 7 from the periodic table, touches 1 line and 6 dots. So all these chlorines have 0. Now if I do the octet check, right, chlorine has a full octet. All of those chlorines touch 2, 4, 6, 8 electrons. But look at aluminum. Aluminum doesn't. Aluminum is only touching 3 bonds, right? This is what we call, right, first off, not full octet, right? This is a non-full octet. You saw this with hydrogen. Remember, hydrogen only wanted 1 bond in a Lewis structure, or wanted a duet of electrons. Some things like aluminum don't need to go to 8 either. Their formal charge is at 0 without doing that. And so they're fine, thank you very much. They want to be left alone. Other things like sulfur have the other option. And look, this version of sulfur in oxygen, in SO2, has 6 from the periodic table, 2 lines, 4 dots. So oxygens have a formal charge of 0, and the sulfurs, sulfur is 6 on the periodic table, 4 lines, 2 dots, equals 0. So those 18 electrons are distributed in a way that got 0 formal charge. This is the rule I like. 0 formal charge is important. But you notice that sulfur has an expanded octet, right? More than 10 electrons. So sometimes when you minimize formal charge, there are some elements that will do that. And the rule is period 3 and below. Why? Because period 3 and below can have d orbitals, and d orbitals are extra space for electrons. Period 1, row 1, and period 2, row 2 won't do that, but period 3 sure will. So we can have diminished octets, unfull octets, and we can have expanded octets. Let's practice just a couple more. So pause and try. and then I'm going to go ahead and display the answers for you. Hopefully we can come up to the same place. All right, here's the ICl4 minus ion. First thing I want you to notice is that because it's an ion, when we calculated our valence electrons, we had to add an extra one for the -1 charge. So that might be one place that you need to pay attention when you do ions. Another thing, because it's an ion, I stuck it in brackets and I put the charge outside. The structure itself has all the chlorines around the iodine, so the least electronegative in the middle. The chlorines each have 1 bond and 3 lone pairs, which gives them a formal charge of 0. That's what I wrote in red. And then the iodine in the center has 4 bonds and 2 lone pairs. And so it ends up being in the, a formal charge of -1. That's good because the whole molecule has a -1 charge. So somebody had to have a -1, and iodine is the one who took it. Let's try this next one. Let's try BrCl3. Pause the video and see where you end up. All right, so here's our bromine trichloride molecule. And there's 28 electrons. So I hope that you've arranged them with the bromine in the middle because it's the least electronegative, with single bonds to the chlorines. All the chlorines have 3 lone pairs each, and the bromines each have 2 lone pairs. When you do the math out on the formal charge for all of those, they all come out with the formal charge of 0. This is a structure that minimizes formal charge. Notice that both of these are examples of that expanded octet I showed you on the previous page, right? Iodine touches more than 8 electrons, and so does bromine, but it doesn't matter because they're big ones from the bottom of the periodic table. Here's another set of examples to try, and these involve some slightly higher order molecules, so I'm going to run you through them. As far as H2CCH2, I want you to notice that the way that that's written has the carbons in the middle, and then it kind of looks like units, that these 2 belong with this carbon and these 2 belong with that carbon. It's a condensed structural formula, and so that is actually what we want to do, is set up our structure like that. And if I count them, if I have 2 C's and 4 H's, I have 4 times 2 valence electrons, and then 1 times 4, so I have 10. Right now I've given 8, and if I do my octet check and I know what I know about hydrogen, the double bond goes here. And if I do my calculations, I promise you, and you should pause the video and try this, they will all come out to 0s. So this is a good structure. And you notice that there's a carbon in the middle here. If you keep one rule in your head that will make Dr. Klein so very happy, or Dr. Watson so very happy when you take organic chemistry, carbon makes 4 bonds. Do not ever attach more than 4 bonds to carbons. Otherwise, carbons are unhappy, and so are your organic chemistry professors. Let's look at one more. Let's look at nitrate. So N has 5 oxygens, 6 each times 3, and then the 1 minus charge adds 1 more. So I've got 18, 23, 24. I put my nitrogen in the middle because it's the least electronegative. I put the oxygens on the outside. And I've distributed 6 so far, so I have 18 more to give away. 2, 4, 6, 8, 10, 12, 14, 16, 18. When I do my formal charge check, though, this isn't very good because I've got -1s on all my oxygens, and I've got a +2 on the nitrogen. It has 5 from the periodic table, and then I can take away 3 for the bonds that it touches, and it's got +2 left. This is not a good formal charge thing. If I erase a bond and convert it to a double, though, it sure looks better because doing that takes this oxygen down to a 0, and it takes this nitrogen down to a +1. That's as good as it's going to get at this point because this nitrogen is now touching 2, 4, 6, 8 electrons. So that's not going to get any farther. But it was kind of arbitrary that I picked this oxygen on the left. I could have just as easily drawn this structure or the one at the bottom. Right, all of those, and I should be a good girl about this and put all of them in brackets and put my charge on them. All of those are valid Lewis structures. And so we're kind of in a quandary. Which one is the right one? And the answer is yes. I know that's unsatisfying, but check out my next video on resonance and we'll talk more about that later.